Hello, and welcome back. Today we'll be continuing with the collision detection pipeline, picking up from where we left off with the last video, which was talking about creating the bounding colliders. Now we're moving to the next step, which is detecting actual collisions. So this is done in three main phases, and each of these phases serve a very distinct purpose. The first of these phases is the broad phase, and the purpose of the broad phase is basically to cull collisions that we know cannot happen. After the broad phase, we move into a very aptly named mid phase, and this likewise can be thought of, instead of collision culling, can be thought of as triangle culling. And then finishing off in the final phase, which is known as the narrow phase. And this is where we do the actual contact generation. So let's start here in the broad phase. We begin by making some decision about what shape we want to use. And it can be an AABB. We can even use OBBs if we want, say, support rotation, spheres if you want to be cheap, or we can even do capsules, right? It doesn't really matter. We want some simple shape. And then we're going to feed these shapes into some acceleration structure. And we briefly touched on this last time, where we talked about speeding up your collision queries to, I believe it was log n or n log n, one of the two, but using a BVH. You also have other options. You can use something like a quad tree, which kind of recursively subdivides space across a grid like that. Or, and this is something we'll actually use later, which is kind of like the big brother of a quad tree, which is an octree, which is, instead of 4 dimensions, as quad suggests, it's 8 dimensions as denoted by oct. There are more acceleration structures, but these are some of the pretty common ones. And the only two that we'll be using are BVHs and octrees. And here in the broad phase, we're really only focusing on the BVHs. So if you recall, we have 3 sets of BVHs in Manifest's collision detector. There is one set for dynamic, one set for static, and then one set for just terrain. This means that we need to have 2 broad phase tests, one for internal collisions, and then one to handle external collisions. It would help if I could spell. The internal only needs to be ran against the inner volumes of the dynamic tree, where the external needs to be ran against the roots of the dynamic tree against the static and the terrain tree. Now, the results of this are going to be, go ahead, bring this up a little bit. The results of this test are going to be a structure I call a potential collision. And this potential collision has 2 collider pointers for the 2 objects. And then it also has a vector of triangle pointers. And these will be brought up again in the mid phase. But for now, when we're doing our tests, if we detect that there is in fact overlap, then we need to say, is this an overlap where one of the colliders is a mesh? If it is a mesh, then it needs to go into a vector of potential collisions that are mesh collisions, and if it's not, it goes into a vector of potential collisions that are non-mesh collisions. And this brings us into the midphase. So the midphase, we're going to pipe in our set of potential mesh contacts. And before I go too further with that, I want to talk about the literature. So a lot of the times in the literature, you'll see the midphase not only does triangle calling, but it also kind of does some pre-processing of your contact generation. It's absolutely fine. I chose to not do that here. I just think it makes the code a little awkward to be doing contact generation in two places and then bouncing that across. It's absolutely fine though if you want to do it. It's what the literature says. It's what's been done. I just wanted to state that. But getting back into this, really, the midphase can be thought of as a very simple statement, which is we want the set of potential triangles, which are the triangles in the mesh that we are colliding against, where for each chunk or triangle chunk in the mesh collider, there exists some intersection between the chunk and some non-mesh collider, which is really just a fancy way of saying in the broad phase, we had BVH and BVH, and we collided the two. Here in the mid phase, we need to take our non-mesh BVH or our non-mesh BVH node, and now we need to use the bounds and see where in the octree for the triangles do we land. And then in any part of the octree, if there exists an intersection between the bounds and that particular triangle chunk, and you can think of a triangle chunk in the mesh colliders as simply just the leaf nodes. So we're detecting leaf nodes. Here, we're also detecting leaf nodes. It's just when we detect a leaf node in this sense, we go ahead and copy all those triangles into the set of potential triangles, and that is synonymous with this vector here. So that leads us into our last phase where we've pruned our contacts that we know cannot happen. We've pruned the triangles that we know we can't be contacting as well. Now we're going to go ahead and do some high fidelity contact detection methods and go ahead and generate the contact points. So I may have shown this before, but this is the contact tree. This will be essentially the list or the table of all potential collision encounters that we can have. And this comes straight from Dirk's GDC talk. So there's really not much more to say except there's 9 individual overlap tests, all of which he does an excellent job explaining, a better job than I can do. I will just say that most of it boils down to finding a point and then creating a virtual sphere around that point, and then testing if the distance between 2 points is less than the combined radii of the 2 virtual spheres. It's not that in every case, but more or less that's what it boils down to. However, I will say one more thing. Contact generation is essentially 3 parts. It's a collision normal, it's a overlap interval or your interpenetration, and then it's also a set of contact points. And these two come from your sphere versus sphere. So it's really not that difficult, but in most cases, getting the set of contact points is not a trivial task. The narrow phase really exists on the back of 2 tests, GJK and SAT. Those 2 tests do a lot of the heavy lifting for handling the robustness needed to do sphere Hall, Hall, capsule Hall mesh, capsule mesh, actually sphere mesh. So for a lot of the meshes, you don't call these directly, but you still use the theory. However, I'm getting ahead of myself. That's kind of it though for the overview. In the next video, I'll be going back into the contact detector that we were using when we made the colliders, building up the phases, and after that, I will be dedicating an entire video specifically to how I implemented the overlap tests because they are, again, they're not the most difficult thing in the world, but simple should not be misconstrued as easy. For that, GJK and SAT will be a black box. Directly after that, I plan on going back to this format where there's a theory video and then a code video, and I'm going to, in detail, go over GJK and SAT because really when I was doing them, I did not find many good resources. There were a handful out there, and luckily, they were able to point me in the right direction. But after that, we really just have the resolver left, and then we should be done with the physics update. And I think that's about it. So if you feel like I left anything out, or if you have any questions that need answering, please let me know, and I will see you in the next one.